Hi, I'm Niels Bohr. Niels Bohr. And your teacher asked me to talk to you about section 5.3 and 6.1 because I know all about it. So, you know, when I was working on this kind of stuff, we'd had different models up to that point. We had the Dalton model. Hey, it must be a ball, sphere, whatever. Then we had Thomson, Thomson, a little plum pudding or something, have some electrons stuck in the pudding. Mm, good stuff, but not right. Okay. And then, my friend Ernest Rutherford had that. Oh yeah, it's a planet. Planet's going around the sun, right? No, that doesn't work because if that were the case, all those little electron planets would spiral into the nucleus. We'd have a whole bunch of black holes all over, and we don't. So I had to come up with a solution to that. And, and I was also trying to explain, see, we have this other thing going on, which we call the atomic emission spectrum. In other words, if I take some electron or I take some elements and I heat them up, they give off light. And we could run that light through a prism and we could break it down into the different colors, and nobody could explain how that worked. Why do we get those colors when we do it? So I came up with this great idea. This is what I said. I said, well, what if let's take that planetary model a little bit, but make it better, of course. And what if this electron jumps out to here, to that next level, because you added some energy, that heat, you put it in there, and then that electron goes back down. And when it does that, of course, it has to get rid of that energy somewhere, because my model, there's only certain levels you can be in. And when it did that, that energy related to one of those lines in the spectrum. So if the electron had gone from here, let's say, down to here, maybe that would be that line. Or if it had gone from here down, maybe that was that line. And my model was so good, it even predicted lights or lines that we couldn't see that were ultraviolet and infrared, and we could go test for them, and sure enough, there they were. Perfect. It worked. Great. So this is what I'm saying. I'm saying that we've got different energy levels. It's kind of like steps on a ladder. You can't be in between. You can only be in those different levels. So I could be on the first step, okay? Or I could be on the second step, or I could be on the third step. Now, I know what you're saying. You're saying, how come he doesn't have shoes on? Well, I didn't really plan this very well, and I like to be comfortable when I do these things. But you can see I have those different levels, and that's the only place you can be. It's quantized. It's only certain increments that you can have. You can only be in those different levels. And sure enough, when I did my calculations, it worked perfect. So when I'm talking about hydrogen, it could explain the colors of the spectrum. Now, some people think there's a problem with mine. Hey, it only worked for hydrogen. Yeah, that's true. It did. My calculations only worked for hydrogen. But, it worked for hydrogen. That's good. And it explained these atomic emission spectrum, and that was huge. Okay, and I get it that I never explained why there are energy levels. I just said there are, and guess what? There are. Okay, I didn't have to explain them because you know what? I still got a Nobel Prize, even though I didn't explain all those things. And I know there's another one where it says, well, according to my calculations, the electron should always be a certain distance from the nucleus, and we know that's not true. We can measure that. All right, so I didn't explain three things or three problems. It only worked for hydrogen. It didn't explain energy levels, and it didn't talk about why electrons are not all in the same distance from the nucleus. I get it. But hey, it was good enough. Like I said, won me the Nobel Prize, and that's really the main thing. Now, I know you'd rather probably hear about my model, but let's talk about some other things. Let's talk about light. Okay, so in the 1600s, there were two guys, Huygens and Newton, and they had different philosophies. And you know Isaac Newton, right? So he said, hey, light's a particle. And Huygens said, no, it's a wave. And there's a big controversy between it's a wave, it's a particle, and Newton, he's a big shot. So, most people kind of believe him. Well, then along comes this guy named Thomas Young. And Young says, well, what if, we know about properties of waves. We know that waves, when they go through openings, they diffract. In other words, they spread out from that opening. So if you have a wave and it goes through these two openings, it's going to spread out, and then it's going to interfere with each other, and you get this kind of an interference pattern, a light and a dark areas where those are constructive interference and not. If it were a particle, on the other hand, you would just get, okay, this is getting hard, you would just get two lines, not this interference pattern. Okay, so Young says, let's take and put two slits in an object and shine light through it and see what it does. And when he does that, he gets this interference pattern, which at that time, this is 1600s, shows, hey, light is a wave. And it pretty much kind of ends the conflict until the 1900s. And then a couple of my friends, Planck, Einstein, these guys are smart people. Probably not as smart as me, but they're good. Planck is working on, believe it or not, he's trying to make a better light bulb. And he's looking at what they call the ultraviolet catastrophe. And he's trying to explain why the light, or the energy, which should just kind of continue to increase as we get hotter and hotter objects. He's looking at black bodies, which in other words, he's taking an object and heating it up. And whenever it heats up, it gives off light. And we would think that energy would just increase continually. But what we find out is it really doesn't. It kind of goes like that. It increases for a while and then it doesn't. Well, Planck says, well, I can explain that if I say that light is quantized. In other words, energy is quantized. It's only in little packets. And he says it's quantized in a little packet, which we now call Planck's constant. It's a really small number. It's 6.6 times 10 to the negative 34th joules seconds. Okay, so a really small amount. But he's saying that you can't have everything. So like if you think of like a wave, it's all that, it's continuous, right? He's saying, no, it's little packets. You can only have certain increments on it. And this has some implications. What it says is that, for instance, you can't go any speed that you want to go. You can go this speed here or this speed here, but you can't go that speed in between. You can't go in anything in between those two. Now, that's really, really small. So small we couldn't ever tell the difference between it because, hey, this is a really small number. And so we don't know. But that's what he's implying, is that there are only certain increments that you can be at. And he comes up with this formula, energy equals his constant times frequency. And basically what this says is the amount of energy that a light gives off depends totally on its frequency. So whatever the frequency is, that's what it is. So what you need to know is that you need to know that there's this idea of black body radiation, which now is going back and supporting the idea that light is a particle. So we said up here, well, light's a wave. Young said that. Well, now Planck says, well, you know what? This works only if light's a particle. And then Einstein comes along, and he's studying what's called the photoelectric effect. Think of like a solar panel. You got light that comes on it, and electrons are given off. That's energy, electricity. Well, Einstein is studying that, and he finds out that you can only do it with you have to have a certain frequency to do it, and kind of confirms this idea that light is quantized. And this is the first, Einstein kind of starts talking about things called photons and things like that. And so this is the very beginning of that. And so these two ideas show that light is a particle. So that's what you need to know. That's the main thing, plus this formula. You got to know that guy. Know that black body radiation and the photoelectric effect are the two reasons, or the two things that show evidence that light is a particle. So now, what we believe, light is a wave and light is a particle. It's both. We think light is both of those things. And, and it acts as one depending on what it needs to be. It travels kind of as a wave, but when we observe it, it acts like particles. And I tried to convince my friend Einstein about this for a long time. He didn't always believe that. We had some good discussions about it, but in the long run, I'm right.